we're going to go over 4 examples of vector mathematics. In the first one, there are really 3 parts, and we've got some scalar multiplication. Our vector q is vector with magnitude 3, and it's in a direction of 30 degrees from the horizontal. And you're tasked with finding the product 3 times q. For scalar multiplication, we just multiply the magnitude. The direction is unchanged, or the line of action is unchanged. If we are multiplying by a negative number, the direction could be reversed. So anyway, in this case, 3 times q is just 3 times 3 for the magnitude, and the same line of action, same direction. Second example, we've got a vector p, and it has a magnitude of 18, and it's acting in the direction up. You're supposed to find 1/2 p. And again, scalar multiplication, we don't change the line of action, just the magnitude. So 1/2 the magnitude is 9, and the direction is still up. For the third example, on this example, we want to do vector addition. All we're given is that this vector r is the sum of vectors a and b. Okay, so we know that about r, and we want to find out what 5r is. Oh, I'm sorry, this is still scalar multiplication. So we want to find out what 5r is. We're going to use the distributive property. 5 times the vector r is 5 times the sum of a and b, and so that's 5a plus 5b. Example 2, we want to resolve the vector m into its Cartesian components, mx and my. We're given that the vector m has a magnitude of 8, and it's acting in a direction of pi by 4 radians, or 45 degrees, and we're supposed to find the x and y components. Here is a picture of m. You can see it has a magnitude of 8. Well, it's kind of hard to see that, but anyway, it does, and it's acting at an angle of pi by 4. And let's see, here it is resolved into its x and y components. We've got m sub x acting in the x direction, so that's a vector with magnitude m sub x and direction of I hat, which is the unit vector in the x direction. And likewise, we have the y component is m sub y times j hat. And we are tasked with finding these magnitudes, mx and my. So we're just going to use trigonometry. Mx is 8, which is the magnitude, times cosine of pi by 4, and my is the same thing, well, 8 times the sine of pi by 4. So here is vector m rewritten in its Cartesian components. Example 3, we have some vector addition. We are given 2 vectors, and we want to find a third vector. So this position vector 2a from the origin is 7, has a magnitude of 7, and it's acting in the direction up. And this vector 2b from the origin has a magnitude of 3, and it's in the direction to the right. So here's that in the picture. Here are those 2 vectors. Position vector 2a from O and p sub bo. And we're supposed to find p sub ba. Maybe that wasn't really clear in this what's given. P sub ba is the position vector 2b from A. So that's not really too clear in what's written up here, but I'm telling you, P sub ba is the position vector, or is the vector to point B from point A. And here it is drawn out. There, that maroon line is, or maroon vector, is P sub ba. And if you look at this, this looks like the head to tail technique for vector addition. So we've got the head of PAO connected to the tail of PBA, and the sum of those, or whenever you do that, you get PBO. So here that is written algebraically. P sub BO is the sum of PAO and PBA. Just looking at this picture, we could write this equation, because we know this is how we can do vector addition. We connect the tail of one to the head of another. So there you go. So now we just need to rearrange that equation to solve for P sub BA, and that's equal to P sub BO minus P sub AO. The final example, we are again supposed to do vector addition. This time we won't do it graphically. We're going to resolve these vectors into their Cartesian components. RC has a magnitude of 10, and it's acting at this angle in radians, and R sub D has a magnitude of 13, and it's acting at a negative 0.395 radians. And we're supposed to find the vector sum of R sub C and R sub D. And the way we're going to do this is decompose the two into their Cartesian components, or resolve them into their Cartesian components. So R sub C, here are its components, 6 horizontal and 8 vertical. And R sub D is 12 horizontal and negative 5 vertical. Might have been nice to have a picture just to look at, but the problem can be solved algebraically. And just a side note, these triangles are Pythagorean triples. One example is 3, 4, 5. Pythagorean triple is a right triangle where the lengths of the sides are all integers. So if you have a right triangle with one side 3 and one side 4, then the hypotenuse is going to be 5. Another Pythagorean triple is 5, 12, 13, where this right triangle has one side 5, one side 12, and then the hypotenuse is 13. And these two, R sub C and R sub D, just happen to be Pythagorean triples. It's clearer to look at R sub D, so the magnitude is 13, and then the two sides are 12 and 5. So 12, 5, and 13 makes a right triangle that's a Pythagorean triple. And then 6, 8, and 10 is just double this Pythagorean triple. Now, back to the problem. We're going to add up the Cartesian components. So we want to get vector P, and its x magnitude is the sum of the magnitudes of the x components, and its y component is the sum of the y components. So we have sum of the x components is 6 plus 12, and the sum of the y components is 8 minus 5, and we end up with the vector P is 18 in the x direction and 3 in the j direction. And those were 4 examples looking at different operations in vector mathematics.